Dear students, today we will see the V and inverter curves for synchronous motors. What will be the variation that happens if you vary the excitation or the field current in the case of synchronous motor? Dear students, as we all know, synchronous motor is a doubly excited machine. And when the electrical energy is converted to mechanical energy in an electrical motor, the medium of conversion is magnetic flux. So there should be some amount of working flux in order to convert an electrical energy to mechanical energy. In synchronous motor, there is a DC excitation given to the rotor side and it produces north and south poles alternatively. And on the stator side, there is an AC excitation given, and since it is polyphase or three-phase supply that is given, it produces a rotating magnetic field. And the principle of operation of synchronous motor is the magnetic locking between the rotor magnetic system and the stator rotating magnetic field. And if the flux that is produced is just sufficient for this magnetic locking, then we can say it is normally excited and the machine operates at UPF or unity power factor condition. When we were discussing on the effect of change in load on synchronous motor, we had seen the change is not in the speed but in load angle. When the load, that is the mechanical load on synchronous motor increases, the load angle also increases, and if it goes beyond a particular limit, the machine will come to a standstill condition or it will be out of synchronism. Now we will have to see what will be the effect of excitation on a synchronous motor. As I had already mentioned, if it is an excitation just sufficient to produce the working flux, then the motor operates at unity power factor condition. And if the excitation is reduced, if it is below a particular limit, what happens is it requires an additional flux or an additional magnetizing current should be drawn from the supply, that is from the AC supply. Since an additional magnetizing current is drawn from the supply, the machine will be operating at lagging power factor condition. And we should be keeping in mind the load on the machine is not yet changed. That means on under excitation, that is below a particular limit of excitation, the machine will be operating at lagging power factor condition. What happens if the excitation is above the particular limit? That is, the excitation current or the field current is increased in order to get a flux, magnetic flux above the required working flux. Then again, from the AC supply, the motor will be drawing a current and it will be a demagnetizing current because we have an increase in field current that is provided to the synchronous motor. And the condition is called overexcitation, And since there is the demagnetizing current that is drawn from the supply, the machine will be operating at a leading power factor condition. We will now analyze the same with the phasor diagrams. That is the role of excitation on the power factor of the machine as well as the load current. The phasor diagram that is shown is for UPF condition, and here we consider the supply voltage V and the excitation E or the induced EMF in the case of synchronous motor to be equal in magnitude. And for all the analysis, we consider the load angle delta to be constant and the angle theta, that is the angle between the resultant voltage ER and I, to be constant, that is given by theta. That is the impedance angle. Since V and E are equal in magnitude, we consider it to be the normal excitation condition. And the phasor diagram, we find the resultant voltage of E and V, that is given as ER, and the actual current I lags by an angle theta. And since it is UPF condition that is given, I as well as the active component of current which is in phase with V, generally we say it as I cos phi, where phi is the PF angle. And in all the analysis, we consider I cos phi to be constant, that is the active component of current. Or when we consider I cos phi to be constant, for V to be constant, then the input power, that is Vi cos phi, remains the same. Now we will consider a case where E is greater than V, that is the condition of overexcitation. We find out ER, the resultant voltage of E and V, and with the same angle theta, with a lagging angle, I is drawn and the angle between V and I is given as phi, the power factor, and we can see the power factor is leading one and I cos phi is kept constant. And we can find, comparing with the previous case, that is the normal excitation condition or UPF condition, the magnitude of I is increased. That means the armature current increases for the motor, but the active power input remains the same because I cos phi is same as that of the previous one. And Vi cos phi remains the same. And the load angle delta remains the same. Here the difference is E is greater than V, that is overexcitation condition. So for overexcitation condition, the motor operates at a leading power factor condition. Now we will analyze the case of underexcitation, that is the voltage E is less than V. Even in this case, we consider the load angle delta to be the same as that of the previous conditions. Here the resultant ER is found out from E and V, and the current I2 is obtained by a lagging angle theta with respect to ER. Theta remains the same as that we had in the previous case, that is the impedance angle itself. And we can find the magnitude of I2, the current, that is the armature current, is greater than the current that we had in unity power factor condition. And here also we consider the active component of current to be the same. So the active power input to the motor remains the same. At the same time, for under excitation, the current is a lagging one. That means the motor operates at a lagging power factor condition. From these three cases, we can understand for normal excitation, the machine operates at unity power factor, and if it is overexcited, the synchronous motor operates at leading power factor condition, and for under excitation, the synchronous motor operates at lagging power factor condition. That means for the same power, the synchronous motor can be operated at different power factors by changing the excitation. That is why the synchronous motor is called synchronous condenser, or one of the applications of synchronous motor is the power factor correction. The above three cases of normal excitation, under excitation and over excitation we will analyze once again. We will consider the synchronous motor to be connected to an infinite bus. Hope you remember what is meant by an infinite bus. Infinite bus is a system where we have a constant voltage and a constant frequency. We have the equation for the mechanical power output for synchronous motor, that is for cylindrical type 1, as P out equal to EV sin delta divided by XS. There is a per phase output, and the power input to the synchronous motor, that is given as Vi cos phi. Here V is constant because it is connected to the infinite bus. And not to have P output to be constant, or the mechanical power output from synchronous motor to be constant, E sin delta should be constant. By manufacturing, Xs can be considered to be constant. And P in, that is the electrical input to synchronous motor to be constant, I cos phi should be constant because B is already constant since it is connected to infinite bus. And the general voltage equation for synchronous motor can be written as V equal to E plus J IXS. Here also remember Ra is considered to be negligibly small. We will consider the effect of varying excitation, keeping the input power, that is Vi cos phi, and the output mechanical power from synchronous motor, that is EV sin delta divided by XS, to be constant. For the same, I cos phi and E sin delta will be constants. We will analyze the case for UPF, lagging power factor and leading power factor. So in this case, here we have the UPF condition where the supply voltage V and the armature current I are in phase, and we have already considered the resistance to be negligible. So V minus J IXS is equal to E. And for the analysis we consider two locuses, that is current phasor locus and E phasor locus. Current phasor locus is vertical and E phasor locus is horizontal. The lines that are shown in the figure or in the phasor diagram One is vertical and the other is horizontal. And now we'll consider the lagging power factor condition. Here I1 is lagging with respect to V by an angle phi1, and the phasor diagram is completed with the phasors minus j I1 xs to find out what is E1. That is V minus j I1 xs is given as E1, and the angle between V and E1, that is the load angle, is given as delta 1. And the locus remains the same, and we can see in the previous case for unity power factor the current was in phase with V and the magnitude of current in that case, and the active component of current here in this lagging power factor condition, that is I1 cos phi 1, will be the same. And we know the input power, then here it will be Vi1 cos phi 1, and the previous case the active power is Vi itself, and cos phi equal to 1 will be equal. Similarly, here E1 sin delta 1 will be same as that of the previous case in magnitude, that is E sin delta. That implies the power output from synchronous motor also remains the same as that of the UPF condition. And here the current is a lagging one. Now we will consider the leading power factor condition. Here I2 is the current which is leading by an angle phi 2 with respect to the supply voltage V, and we have E2 as V minus j I2 xs, and the angle between V and E2, the load angle, is given as delta 2. Comparing with the previous case, E2 sin delta 2 is equal to E sin delta and is equal to E1 sin delta 1. That implies the power output in this case also remains the same as that of the previous two cases. And regarding the power input, that is Vi cos phi, here we have Vi2 cos phi 2. Here the active component of current I2 is I2 cos phi 2. So the power input Vi2 cos phi 2 is same as Vi1 cos phi 1 or Vi as that of the previous cases. In this slide, there is a combination of the previous three cases, that is unity power factor, leading power factor and lagging power factor conditions that are combined, and it is given. We can understand from the diagram E sin delta remains the same. That implies the output power from the synchronous motor, even if there is a change in power factors, remains the same, and the input power remains the same as Vi cos phi or Vi1 cos phi 1 or Vi2 cos phi 2. Now if we analyze these three cases from the phasor diagram, it is clear. For unity power factor condition, we have an excitation E, and for lagging power factor condition, the excitation is E1 and it is less in magnitude compared to E, the unity power factor condition. And for leading power factor condition, the excitation is E2 and is greater in magnitude compared to the normal excitation E as that in the case of unity power factor condition. So by keeping the power output and the power input to be constant, by changing the magnitude of excitation, there will be a change in armature current and there will be a change in power factor also. And at UPF condition, the magnitude of armature current will be minimum. And if it goes to the leading power factor condition or to the lagging power factor condition, by change in excitation, the magnitude of current will be increasing. So the same is explained here. For normal excitation, it will be having only an active component of current. For under excitation, there will be a magnetizing current that is additional, which is drawn from the AC supply, which makes the machine to operate at lagging power factor. And for overexcitation, again there will be an additional demagnetizing current that is drawn from AC supply and makes the machine to operate at leading power factor condition. This I have already explained. For different excitation, the armature current as well as the power factor varies. The armature current will be minimum for UPF condition and there will be a change in power factor whenever there is a change in excitation, and along with that the armature current also will be increasing for both leading power factor as well as a lagging power factor condition. So the curve which shows a relation between the variation of armature current with respect to the field current is named as V curve, and a curve which shows the variation of power factor with respect to the field current is named as inverted V curve, and the name is because of the shape of the curve that is obtained by the variation of field current for armature current and power factor. Keeping the load to be constant and the input power to be constant, we can plot the change in power factor and current with respect to the change in field current or the excitation, and that gives the V curve and inverted V curve for synchronous motor, and that is shown in the figure. And for under excitation, from the figure it is clear and it is marked as lagging power factor condition, and for over excitation it is leading power factor condition, and normal excitation is given as UPF. And the variation of armature current, for lagging power factor the current is higher, and when it comes closer to the normal excitation, the armature current magnitude will be getting reduced and will be minimum at UPF condition. And when we move to leading power factor condition, again the magnitude of armature current will be increasing. So for different load conditions, we can plot V curves. For each V curve, we will keep the load to be constant and we will vary the field current to get the V curve. And for different loads, we can find out the points at which the equal power factor occurs, and that is plotted in the graph that is given, and that is what is given as compounding of curves. From the graph we can understand what should be the variation of the field current in order to get the same, or in order to keep the power factor to be constant for different load conditions. Here we have the experimental setup in order to find out or to plot V and inverter V curve in the case of a synchronous motor. On the left side we have a DC motor. Initially the motor or the machine, DC machine, will be operated as a motor, and later it will be operated as a generator. And on the right side we have the synchronous machine. Initially it will be operated as a synchronous generator or alternator, and later it will be operated as a synchronous motor. And on the bottom side you can see the field winding of synchronous machine. The synchronizing switch is kept at open condition, and on the left side we have the DC machine, and that will be operated as a motor initially, and the supply is provided, the DC supply to DC motor, and by using a 3-point starter the machine is operated, and the field current will be adjusted by using the field rheostat given, and the machine will be operated at a speed closer to synchronous speed. At that condition the field supply will be given to the synchronous machine too, and the synchronous machine will be operated as a synchronous generator or alternator. And as we know, the machine will be connected to the infinite bus. Here we have the 3-phase supply on the right side that is given, and since the machine, that is synchronous machine, is operating as a generator, there will be EMF that is induced, and we can synchronize the machine with the AC supply, and you can close the synchronizing switch. Now the machine will be at a floating condition, and the DC supply given to DC machine can be cut off. Then the synchronous machine will be operating as a synchronous motor. Now DC motor or DC machine will be acting as a DC generator. There is no load that is connected to the generator. Now we can vary the excitation given to the synchronous motor, and we can find what will be the current that is drawn from the supply and what will be the power that is taken as the input to synchronous motor, and we can plot correspondingly the V and inverter V curves. And for another load condition, we can close the switch on DC generator side to the loading rheostat, and we can vary the load and keep it at a constant condition, and we can plot the same V and inverter V curve for that particular load condition too. So today we are discussing on what is the effect of excitation on synchronous motor keeping the power a constant. We have seen there will be a variation for the armature current, and correspondingly there will be a change in power factor too. By changing excitation, the machine can be operated at different power factors. Thank you.